Jai Hind, welcome to the course Network Analysis and Synthesis, and today I am going to discuss about the steady state response of a network when it is applied to a sinusoidal input. In the last lecture, we discussed steady state response of a network when it is applied to a periodic non-sinusoidal signals. We discussed what are the different approaches to find the steady state response when the network is applied to a periodic non-sinusoidal signals. So today in brief just we will discuss those methods and then we carry out some examples to find the steady state response of a network when input is sinusoidal. So to find the steady state response of a network, whether the input is sinusoidal or non-sinusoidal, there are two methods. One is the direct Phasor approach and another one is the spectrum product approach. So in direct Phasor approach, what we do, we just convert the circuit in Phasor and carry out all the analysis in the Phasor. In the last, we convert back to the time domain. So basically it is representing this product of the network function and Phasor excitation. So it is the product of the network function. So network function, so network in S domain, or we can say the frequency domain, and Phasor representing the excitation. So it is the product of the network function. So there are different type of network functions. They may be the driving point admittance function or they may be the transfer function. So we find the network function and take the product of the network function and the excitation function. So this is the direct approach. So there are three steps. What we do, just first we convert the given circuit into Phasor. All the elements are converted into the Phasor, whether either the active elements or the passive elements. Then we carry out all the analysis in Phasor, and in the last we convert back to the time domain, and that represents the steady state response of a network. Whereas in spectrum product approach, what we is the magnitude and phase spectra of the excitation together with the network function. So first we calculate the magnitude spectra separately and phase spectra separately. So for the amplitude spectra of the response, it is the product of the magnitude of network function and amplitude of the excitation spectrum. So we take the magnitude of the network function and amplitude of the spectra of the excitation and take the product that will give the magnitude. And for the phase spectra of the response, we measure the phase angle of the network function and phase angle of the excitation, add it to get the phase angle of the network function. So in direct approach, we convert the circuit in Phasor, carry out all the analysis in Phasor, and in the last we convert back to the time domain. Whereas in the spectrum product approach, we find the amplitude spectra and frequency phase spectra separately. So all these details we discussed in the last lectures. Today I am going to take the problems on steady state response of the network when applied to a sinusoidal input. So the problem is like this. Suppose find the steady state current, steady state current through 2 ohm resistor using Phasor. The problem can be fabricated in this manner. So thus the circuit is like this. So this is your so this is the given network. It is 20 millihenry inductor and this is 2 ohm, and we have to find the current through this. Current through this is 1 millifarad and this is the 5 ohm, and the excitation is sinusoidal and it is given as 4 cos 100t minus 20 degree ampere. So this is the given problem, and you are required to find the steady state response. So what are the steps? So steps are convert the circuit to phasor, then carry out, or you can say the calculate current I through 2 ohm resistor, then convert back to time domain. So these are the 3 steps: carry out, calculate the current through the 2 ohm resistor, and third step is convert back to the time domain, and that is the steady state response. So this circuit can be modified in phasor. So this can be written as in phasor, it can be written as 4 angle minus 20 degree ampere. Okay. This 5 ohm and 2 ohm, they are independent of frequency. So then we have to, what we have to do, we have to convert this capacitor and inductor in phasor. So x is equal to 1 by j omega c. So 1 by j, and omega is here, omega is 100, because it is cos omega t minus phi. Okay. So omega is 100 into 100 and c is 1 millifarad. So it can be written as 1 by j is minus j and it is 10. So minus j 10 ohm. Then XL is 20 millihenry. So 20 millihenry. So we can write XL is j omega L. So j omega is your 100 and L is 20 millihenry. So it is 20 into 10 to the power minus 3. So it is Henry, it is farad. Now it has been converted into ohm. So it is J, or it is basically J, this and this cancel out. So it is J 2 ohm. Okay. So I just will draw the phasor circuit, phasor diagram. So phasor diagram, it will be like this. So it is your current, then we have the impedance of 5 ohm, then have the capacity impedance, then we have the resistor and inductor. So inductive impedance we have calculated J2 ohm, it is your 2 ohm. The capacitive is minus J10 ohm and inductive is J2 ohm. This is your 5 ohm and this is your 4 angle minus 20 degree ampere. So this circuit is in phasor and you have to find the current through this 2 ohm resistor. So if we simplify the circuit, suppose these two elements 5 ohm and minus j 10 ohm, they are in parallel. So just find the equivalent of these two. So it is 5 and minus j 10, 5 minus j 10. So it can be written as, it is coming 4.47. You can check it, it is coming 26 minus 26.6. It is ohm. Okay. So it can be further. This is your this and this. This is your, it is J2 ohm, J2 ohm inductive reactance. This is your 2 ohm, this is the current you have to find, and this is your Z, which is 4.47 angle minus 26.6 ohm, and this is your current, which is 4 angle minus 20 degree. Okay. Why I have converted into a single element? Because the given excitation is current, and we look at it is very easy to apply the current division. So we can apply current division, because this Z and 2 plus j 2 ohm, they are in parallel. So to find the current through 2 ohm resistor, so we can write here I is equal to, so 4.47 angle minus 26.6, this impedance divided by total impedance. So 2 plus j2 plus 4 plus 47 angle minus 2.2 to 26.6. Okay. So this is in phasor form, this is in phasor form, this is in rectangular form. So convert it into rectangular and just multiply it and then take the division. We get the I is equal to, we are getting I is equal to, this I is basically this once we convert it into phasor, so it becomes this I. So this is capital I. So I is equal to, it is coming 2.98 angle minus 46.58 ampere. So this is the current through 2 ohm resistor in phasor form, So now we first step was convert the circuit into phasor, then second step was carry out all the analysis or find the response in phasor, and third step was to convert back into time domain. So we can write, so it is, so we can write, so magnitude is 2.98, okay, and this is the phase angle, So 2.98, then your cos frequency was 100, omega was 100, so 100 t, okay, and this phase angle is minus 46.58, so it is minus 46.58. 46.58. So this is steady state response. Steady state response of the network. Procedure is very simple. If the circuit is purely sinusoidal or excitation is purely sinusoidal, then convert the circuit into phasor, carry out the analysis in phasor, and in the last convert back into the time domain. So take another example. Take another example to find the current I1 and I2 for the network shown below. So the network is like this. Here we have resistor, then we have the inductor of 1 Henry, then one dependent source. It is plus minus 5 I1. This is 0.33 farad, I think, and this is 1 Henry. This is 2 ohm. This is your I1 and this is your I2, and this is your excitation voltage. This is given as 2.5 cos 10 t plus 9. So this is the excitation, and you have to find the current I1 and I2 steady state. So these are the steady state value, steady state currents I1 and I2. So this is 1 Henry and this is 0.33 farad. So just we convert. So here given omega is 10 radian per second. So XL is j omega L. So j into 10 into 1. So it is j 10 ohm. XC is 1 by j omega C. So it is coming 1 by j omega is your 10 and C is 0.33. So it is minus j upon 3.3. So we can write minus j. We can write minus j 0.3 ohm. Okay. And this excitation is in phasor. Excitation in phasor. It is 2.5 angle 9 degree. So this network can be converted into phasor, and it will be like this. So it is coming in phasor form. So it is your voltage. This is your impedance of 2 ohm. This is your inductor. This is your farad. And this is your So we have written in phasor, so it is 2.5 angle 9 degree. This is your I1, this is your I1 and it is 2 ohm, and this is your I2 and it is minus J 0.3 ohm, it is J 10 ohm, and this dependent source is basically it is current controlled voltage source. So it was 5 I1, so it is 5 I1. Okay. So now this is the circuit I can write here circuit in phasor. Now there are two loops. This loop is, say, this is A, this is B, this is C, this is D. So there are two loops. So in this loop the current is flowing I1 and this loop current is flowing I2. So there are two unknowns I1 and I2. So we have to write two equations. So apply Kirchhoff's voltage law in loop A, B, C, A. So this is your plus, this is your minus. So we are moving from negative to positive. So it is 2.5 angle 9 degree minus 2I1, because we are moving from B to C and current is also flowing from B to C. So here is plus, here is minus. So from plus to minus, so it is negative. Then minus J10 I1 minus I2. So I1 minus I2 will flow from C to A and we are also moving from C to A. So this is one equation. Now we have to write the another equation. So apply Kirchhoff's voltage law. Apply Kirchhoff's voltage law in loop A, C, D, A. So A to C. So A to C is J10 I1 minus I2. We are moving against the direction of current, minus I2 minus J 0.3. This is the drop across capacitor. Then plus to minus, so it is minus 5 I1 equal to 0. So there are two unknowns, two equations. So we can calculate I1 and I2. We can calculate I1 and I2. So on simplification, just I am writing the value of, so on simplification, we get I2 is equal to I1 is equal to 0.349 angle 11.47 degree and I2 is coming 0.403 angle 38.1 degree. So these are the currents in phasor. So the last step was convert back into the time domain. So in time domain it is I1t, it can be written as 0.349, okay, cos frequency 10t and this angle 10t plus 11.47 degree and I2t is 0.403 cos 10t plus 38.1 degree. So these are the steady state response. Steady state response when input is sinusoidal. So this way we can find the steady state response of the network when input is sinusoidal. And in the previous lecture we discussed the steady state response of a network when it was non-sinusoidal periodic. Suppose the wave shape is like this, it is also a periodic sawtooth, okay, having the time period 0t, amplitude is suppose say the E. So what you have to do, you have to apply this is your Vt. So Vt, we can find the Vt, find Vt, how will do it? Apply the Fourier series, find Vt and then apply this excitation to the given network, and we can get the steady state response, which we did in the previous lecture. A steady state response of a network when its input is non-sinusoidal periodic. So this is all about your steady state. We finished both sinusoidal as well as non-sinusoidal signals. So in the next lecture we will discuss some another topic. So Jai Hind, thank you very much.